everyone. So we are back with our probability video lecture. And we're going to start with problem 6. So a box contains 3 red balls and 3 green. And it's a good thing because those are the only 2 highlighters I have that work. 2 balls are chosen, and what is the probability that red is chosen first and then green? And what is the probability that 1 red and 1 green are chosen? And there's a subtle difference between A and B. So first we have our 3 red balls. So 1, 2, 3. Then we have our 3 green balls. And 2 are chosen, presumably at random. And we're trying to find the probability that red is chosen first and then green. Well, red has a 1/2 chance of being chosen first, right? So let's say that I do choose a red ball, and there's a 1/2 chance that I do choose a red ball. That takes away this red ball. And so when I go to pick my green ball, I have a 3/5 chance of choosing a green ball. And so that is 3/10. But so this is problem A. But for B, I'll draw back in my red ball. The probability that I'll choose red first and then green is 3/10. We established this before. And then the probability that I'll choose green first and then red is also 3/10. So when I add them together, I get 3/5. And so you can notice that these 2 probabilities are different. So in the first problem, we stipulate that we have to choose red first. For B, it doesn't matter which one we choose first. We can choose red first, or we can choose green first. It doesn't matter. So the probability is higher, and it's doubled the probability of A. Alright, problem 7. John and Jane each choose an integer from 1 to 10 inclusive. What is the probability that they each pick a number greater than 7? So 1 to 10 inclusive basically means 1, 2, 3, 4, all the way up to 10. And so inclusive means that we're including the number 1 and the number 10. If it was 1 to 10 exclusive, we would not count 1 or 10 in our range. What is the probability that they each pick a number greater than 7? So the numbers greater than 7 are 8, 9, and 10. So they have a 3/10 chance that one of them will, okay, here, how about this? We start with John. John has a 3/10 chance of picking a number greater than 7. Those numbers are 8, 9, and 10. And then here, John. And then we have Jane. And Jane also has a 3/10 chance of picking a number greater than 7. So we multiply these 2 probabilities together to get 9/100ths, or 9%. So for example, if you have 2 events happening and they're separate, so the 2 events in this case would be John choosing number and Jane choosing number. If they're separate, you have to multiply their probabilities that each one of them will happen together. Okay, so that was problem 7. Problem 8. If Sophia randomly chooses a 4-digit number, what is the probability that all 4 digits will be distinct? So distinct basically means that all 4 digits are different numbers. So 1, 1, 1, 1 would not be distinct because they're all ones. 1, 1, 2, 3 would still not be distinct because 1 and 1 are not distinct digits. And a good thing to remember when we're doing this problem, problem 8, is to remember that probability of something happening. Probability is equal to the number of good events, so good situations, the situations that we want to happen. So in this case, the situations that all 4 digits are distinct versus the number of total situations. Total situations. So in this problem, if Sophia randomly chooses a 4-digit number, we can figure out how many of those solutions, of those digits, are valid in this problem. So how many of those numbers have distinct digits? and then we can figure out the total number of 4-digit numbers. Okay, so let's just figure out the number of good situations first. Well, the digits we have to choose from, we have to choose digits for 4 numbers, and the number of digits that we have to choose from go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this first number could be any of 9 numbers, excluding 0, of course. So it could be 1, it could be 2, it could be 3, it could be 4, it could all of those numbers all the way up to 9. So our first digit could be 9 numbers. But our second digit can also be 9 numbers because we're including 0 now. So our second digit could be any of these numbers, including 0, but excluding the 1, the number that the first digit was. And so for our third digit, we have 8 options. So it cannot be any of the digits of the first two digits in this number, but it can be any of the other 8. And then for our last digit, we'll multiply by 7 because the same kind of logic follows. It doesn't matter what digits these actually are. What we just want to count is the number of possible numbers for the good situations. And so this is the sum of this. It's going to be a long number. Is going to be the number of numbers that fulfill this requirement of having 4 distinct digits. And then the total situations, well, for the total situations, we have 9 for the first digit because it can only be from 1 to 9. Then we have 10 because it could be any of these numbers, and then for the second digit. And then we have 10 again because it can be any of those numbers for the third digit. And we multiply by 10 again. And so the probability would be dividing these two. And that's mainly why I didn't simplify this first. So if we divide these two, make this 9 a 1, 3, 3, 2 5s. Okay. This is 5 times 5 times 5. We get rid of this 8 here. Yeah. So now in the end we have 7 times 9, which is 63. Yeah, 63 divided by 125. And that's our probability in the end. So in our next unit, we're going to talk more about counting and probability. This week we were more focused on introducing statistics and probability, but you will definitely need to understand this concept here, the concept of counting the total number of good situations and the total number of situations in order to figure out probability. Okay, so for our 9th problem, a Flo Hyman spike puts the ball away 60% of the time. What is the probability that her first spike on a given point is returned and her second is not? Okay, well, this is what we did in the problem before this one I mean. So the probability that her first spike on a given point is returned is 60%, right? So we have 60%. That's our first event. But our second event is that her second spike is not returned. And the probability that her second spike is not returned is 40%. So we just multiply these two together. We get 0.6 times 0.4. That's equal, I wrote 6 here. And 0.4, that's equal to 0.24 or 24%. So when you're doing these kind of problems with 2 events, so the probability of event A and event B is equal to the probability of A times the probability of B. So that's for number 9. Number 10, what is the expected value of a Michael Jordan shot of if 43% are 2-pointers, 6% are three-pointers, and the rest are misses. Alright, so the thing to remember about expected value is that expected value is not the most probable value that you will get, if that makes sense. So here, I'll just do this problem to explain. So the expected value, if a Michael Jordan shot is 43% are two-pointers, so we have 0.43 times 2, plus 6% are three-pointers, so 0.06 times 3, and the rest are misses, so something percent times 0, which is just 0. When we add these two together, we will get the expected value. And alright, 0.43 times 2 plus 0.06 times 3, and that's equal to 1.04. And so this is what I mean by expected value not equaling the value that you will necessarily get. So if your expected value is 1.04, that means that if Michael Jordan keeps on shooting, like he shoots 20 times, you can guesstimate what the sum of all those shots would be. If he shoots 20 times, it would be 20 times 1.04. 1.04 is basically his average when shooting. But you'll never expect that he'll make 1.04 exactly on a shot. That's impossible. He can only make 2-point shots or 3-point shots. He can never get a 1.0 points after a shot. But this is what we think the average would be after he has shot a lot of times. This is what we think his average score for all of his shots would be. And so that's what expected value is. Anyway, guys, thank you guys for watching. Any questions on your homework sets, don't feel free to email us or comment on the assignment.